Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 39, we will talk about stormwater drainage planning, and this is the second part. So, the different concepts that we will cover are on stormwater volume, rainfall intensity, duration, frequency relationship. So, this is one of the very important things that we need to learn about stormwater planning, stormwater drainage planning. Then IDF curve generation, intensity, duration, frequency is IDF, and so the first we will learn about IDF curve generation, then IDF curve generation using Barnard equation, IDF curve generation using probabilistic method, IDF curve generation using Gumbel distribution, and stormwater runoff estimation. So, when we try to determine stormwater volume, we have to understand that only a part of the rainfall generates the surface flows or the eventual stormwater volume. So, why only a part? Because there is infiltration that happens, that means some of the water is infiltrates the ground. So, it depends on the infiltration capacity of that particular soil. It also depends on the depression storage. That means certain amount of water, there are certain depressions on the ground where water is accumulated. Once these depressions are filled, then only the water starts flowing outwards. Some amount of surface detention, and then of course, the surface flow. And this so we can say that the accumulated water on the surface flows over land and reaches streams and river and is known as surface runoff. So, this surface runoff is actually what generates the stormwater volume or the total flow stormwater drainage volume, you can say. So, what factors or characteristics of the catchment affects the runoff? So, as you can understand, the water flows over land and then reaches the point of disposal. So, that means it is going over the land, so or the catchment. So, there are certain things in the catchment which affects the runoff. The size and shape of the catchment has a role, has an effect on the quantity of runoff that is generated. The elevation and slope, of course, of the catchment will also have a role to play. The more the elevation, the faster, the more is the slope, the faster will be the travel time. The drainage density, then type of soil, land use. Type of soil may influence percolation more, for certain soils more infiltration is there. Land use and land cover, imperviousness, that could be determined by land use. Topography, the depression, storages, ponds, lakes, the presence of ponds, lakes and certain undulations in the ground, that is could be dealt, but that could be shown through topography. Then the soil wetness, that means once rainfall happens, then the soil becomes wet. If again rainfall happens, then the soil is already wet. So, it may not have that much amount of infiltration. So, more amount of water becomes runoff. So, that could be soil wetness do have a role to play. Groundwater level in that area, all these things play a role in determining the amount of runoff that is generated by a particular area. So, some of the losses that we also experience are the evaporation losses from the catchment, percolation losses from the catchment, and absorption losses by trees, leaves and so on by the catchment. So, these are the water that is lost whenever water falls on a catchment. So, how do I estimate runoff? So, if you remember from the from water supply, we have learned that the use of rational method, we have used this rational method to determine the amount of runoff. So, if you remember the formula, it was Q equal to CIA by 360, where I was where we were determining that quantity of stormwater discharge or we are saying quantity of runoff in meter cube per second. So, over here it is Q equal to quantity of stormwater discharge in meter cube per hour. So, that is why it is Q equal to 10 into C into I into A. Now, what is C? C is coefficient of runoff. That is the based on all the different characteristics we can give a value and say that okay, so much percentage of water actually is becomes runoff. Then I is the intensity of rainfall in millimeter per hour. What is the intensity of rainfall? That is that means for a certain time period, I was saying earlier that the intensity may vary, right. So, that over here this intensity of rainfall per hour, and this A is drainage area in hectares, that is the total area. So, if the rainfall event is for a longer time, the intensity may be different compared to a rainfall event for a shorter time. Then cross section velocity method is basically when the water actually goes to a stream and then flows along the stream, we can measure the profile of the cross section of the stream, and then based on the velocity of water in the stream, we can determine the quantity of flow over in the or the quantity of runoff as well. So, these are the two methods which we have learnt earlier. So, I am not getting too much into that, but this actually tells us is this is the total amount of water that is generated in that particular catchment. That is, we know that intensity per hour, and that eventually when we do this, we will get the total quantity of stormwater per hour. So, if the rainfall stretches beyond that, then obviously we will have to this particular rate has to be adopted. So, next we will learn about the rainfall intensity, duration and frequency relationship. So, three terms: intensity, duration and frequency. These are related, and that we have to understand the relationship between them. Before we do that, some basic things, that is runoff from the tributary catchment reaching inlets of stormwater drains are estimated in stormwater drainage. So, that means we have a area, we have a drain over here. So, from different parts of this particular catchment, maybe there could be some streams that are generated, and then it comes, and this is where it comes to the main stormwater line, right, or the stormwater drainage line. So, over here this is the inlet point where this water enters into the stormwater drains. So, that means the entire area's water flows along some channels which are maybe natural natural depressions, or you can this could be called as valleys as well. So, within these valleys the water will flow and then reach the inlet point of the drain. So, this is this runoff from tributary catchments reaching inlets of the storm water drains are estimated in stormwater drainage. So, we need to understand these flows. So, once it enters into the drain, it goes underground into the sewer network or the stormwater drain. It could be a closed, in most cases this is a closed drain, or it could be a sewer as well. So, it could be underground closed conduit as well. So, definitely we need to understand how this flows comes, and this is when it is flowing in the catchment or and this is where we need to estimate that the catchment may have an effect on the quantum of water that flows over it. So, rainfall intensity also varies in magnitude and duration in different areas. So, rainfall is not uniformly falls on a particular area, neither is the intensity uniform throughout the rainfall event, neither is it is same in all the areas. So, this needs to be considered. So, this variation needs to be considered, otherwise we may end up designing inadequate drainage systems leading to flooding. So, rainfall could be classified as very light rain, moderate rain, heavy rain, very heavy rain and extremely heavy rain. So, extremely heavy rain is greater than 204.5 millimeter per day, heavy rain is around 64 to 115 millimeter per day. So, you can understand these figures, right. So, these values are this is just some terms that we use to classify different types of rainfall. But we actually need to work with the exact figures of what is the rainfall to determine the stormwater drainage. So, variation in intensity, duration and frequency of occurrence that needs to be measured for any rainfall event, and it is determined by this intensity, duration, frequency curves for a particular area. So, we generate this intensity, duration, frequency curves for a particular area. So, IDF curves are developed from rainfall data of that area, which is basically we use this rain gauges to measure the rainfall continuously over every day for each area, for each station, that rainfall station that we have got, or the for this rain gauge station that we have got in that particular urban area. And this daily rainfall charts of self recording rain gauge stations of Indian Meteorological Department, those are used actually, and these are used to generate the IDF curves. I will show you how to generate the IDF curves, but this is a record of what kind of rainfall event happened and what is the intensity of rainfall per hour for every day. So, that is what we are actually measuring using this rain gauges or the self recording rain gauges. So, this is the rainfall intensity curve. So, rainfall intensity and duration, you can see in this side there is duration, and on this side there is rainfall intensity in millimeter per hour. So, what does this curve signify? This curve signify that this blue line, this is called a 5-year curve, then there is a 10-year curve, then 20-year, 30-year, 40-year. This 5-year, 10-year, 20-year, 30-year, 40-year, this is the frequency. So, now you have got duration, intensity, frequency. I will now explain it in detail. Duration means if the rainfall happens for 10 minutes or if the rainfall happens for 20 minutes. So, what is the intensity of rainfall? So, that means this intensity is not the intensity of one rainfall event, it is the maximum of all rainfall events within a certain time period. So, that time period is the frequency. So, what was the maximum rainfall that happened of 20-minute duration in the last 5 years? So, in that case we will use this particular, the lowest curve over here, this one, right. So, what is at 20 duration? We can see the duration is, the intensity is over here, right, for the 5-year curve. So, if I take this over here, the intensity is somewhere around 35 maybe, right. So, 35, 45, 35 or maybe 30 even. So, this is the intensity of rainfall for a duration of 20 minutes. Why we consider this? So, this is the maximum intensity that has been recorded in the 5-year period. Now, if I want to determine what was the maximum intensity recorded in the 10-year period, obviously, see, for this 20 years the 10-year period curve is higher. So, that means the rainfall intensity that was recorded was maybe 45. So, the more is the frequency or this this years in that particular curve, the 20-year curve or a 30-year curve, the more is the frequency of return of that particular event, higher is the intensity, because there is chance of that kind of this extreme event happening even more. So, the other relationship is lesser the duration, higher is the intensity. So, we can see that for 10 minutes the intensity is 50, whereas for 20 it is 35, for 30 it is somewhere around 22, 23, 27, 26, something like that. So, similarly it goes down when the duration increases. So, few rules, a few summary that we can, if we summarize what we just learned. So, usually higher intensity rainfall are of lower duration. Usually duration is given and we have to choose intensity for the right frequency or return period. So, this frequency is the return period. So, we also call it a return period. So, 5-year return period, 20-year return period, and usually the duration is given. So, we know the duration. In urban catchments duration is small. In urban catchments duration is small. Why? Because we have this drain and we have the catchment area. In urban areas usually there is drains at certain intervals. So, if I have got drains at this intervals, obviously some amount of water will come to this drain, some amount of water will go to this drain. So, what is the catchment of this drain? the catchment of this drain is like this. So, usually we say catchment of this particular inlet. So, this is the inlet, the catchment area which drains into that inlet is something around this, right. So, we are only concerned about this particular area. So, usually in urban areas this is very, very small, right. So, that means the total amount of water that is falls on this particular catchment, and then it comes to this particular point. So, that there is a travel time of water from the extreme part of the catchment to this particular inlet point. So, if I have got a drain and this is the inlet point, this is the second inlet point. So, catchment of this particular inlet is this part, catchment of this particular inlet is this part. So, the time taken by water to travel from this extreme point to this particular point, that is the travel time of water along this particular catchment. So, this may depend on this particular slope of that particular catchment and many other things. So, this point over here is whenever we are trying to determine that what is the intensity of rainfall, what is the maximum intensity possible, of course, for a particular return period, we actually determine that what is the travel time for the entire catchment to reach this particular point. So, we will take the maximum the point which is furthest away, we will estimate the travel time. Whatever is the travel time, that is the time period when rainfall can happen. What is the maximum for that duration rainfall can happen? What is the maximum intensity of rainfall during that duration? So, if that time is around 10 minutes, we will try to determine what is the maximum duration. So, usually because urban catchments are very, very small, we limit our intensity to at least 10 minutes. So, that means that travel time should be at least 10 minutes to some extent, right. So, this is also known as time of concentration. So, time of concentration is basically rainfall to runoff time is small, that means rainfall becomes runoff, it travels along this particular distance, and this time is called as time of concentration. But one more thing, suppose then I am considering this point. So, this is the sewer network. So, this I am considering the next point. So, here water comes from this point, from this particular catchment water comes to this particular point, plus water comes along the sewer lines from this inlet to this one. So, it is not only the water that is coming from the surrounding area, but also water from the previous catchment along the drain. So, time of concentration over here is not only considers, that means everything which is beyond this, that means every area which drains into this point, we have to consider the time of concentration based on that. So, that means time of concentration for this point is the total area, the total time taken by water to travel from this extreme point to this inlet, plus the time it takes to travel from this point to this point. So, some part of the time is the overland flow time, some of the time is the gutter flow time, or this time it takes to travel. So, in this case time of concentration is both time of travel from this point to this point plus from this first inlet to the second inlet. So, this together means the time of concentration. Anyway, we will do this thing in detail in the subsequent lectures. So, we will explain this in more thoroughly, but that is what time of concentration is, and usually time of concentration is the one that we are concerned about. For every inlet the time of concentration is different, and the more down you go, that means this is a first starting point of the first inlet, this is the second inlet time of concentration is the entire area before that. Third inlet's time of concentration is depending on the entire area before that, right, because here the water comes from the entire catchment above it. Okay. So, that is how we keep on estimating the time of concentration for each of this inlet, and determine based on that the water volume that is considered, or the storm water volume that is considered for that particular point has to be considered. So, IDF curves are very, very important that you have understood. So, IDF curves are not readily available for all areas. And as you understand, this IDF curve help us to understand the maximum rainfall that is possible for a certain duration for a certain return period. And that is used for designing pipelines, because whenever we are designing pipelines for stormwater drainage, we have to design it for extreme cases, right. So, IDF curves are not readily available for all areas. This requires analysis of rainfall records to prepare IDF curves to establish intensity, duration, frequency relationship. So, if we have no IDF curves available, then we have to prepare IDF curves. The other thing is the frequency or return period of a storm event may be defined as the average recurrence interval between events equal to or exceeding a specific magnitude. So, if we have a particular intensity of rainfall, we need to understand that the frequency or return period of a storm event may be defined as the average recurrence interval between events equal to or exceeding a specific magnitude. So, what is the average recurrence interval for that particular event or that extreme event, right? So, that we have to determine. So, that means the return period actually determines the maximum possible intensity that is possible in that return period, which has no chance. That means within that time period, that is the maximum frequency that has been observed. Any frequency above that is not that is not observed within that time period. So, that means whenever we have got this IDF, when we have to generate the IDF curves and we do not have the actual curve, we have the idea about what kind of frequency we are looking for, that means what kind of return periods we are looking for. We have to have an idea about the rainfall data that has been recorded over time for that particular area. So, rainfall and we have to do the analysis based on that. So, rainfall analysis is carried out using continuous recorded data for intensity and duration of rainfall event at a station for last 25-30 years or more to prepare IDF curves. So, intensity and duration of rainfall both are recorded in a particular station in every rain gauge station, and this data is available for every day for the last 25-30 years. That has to be taken to generate these IDF curves. So, these curves are updated every 5 to 10 years, and average intensity is used, that is precipitation per time for that time period. Of course, for that particular time duration, we take the average intensity, that is what sort of precipitation and time happened, precipitation within that time happened, and return period depends on criticality of infrastructure. This we have discussed earlier. That means, the more critical a infrastructure like a airport, we will consider 100-year return periods. That means, that storm recurrence interval has to be within 100 years. That means, it can only be returned after another 100 years, right. So, this is what we will, so accordingly we will choose the return period. So, this is like this rainfall is measured by rain gauges, mostly self-recording type, and there are also non-recording type rain gauges, but usually we use self-recording type ones, which measures both the intensity and duration. So, here you can see this is that graph on which this record is there. So, this line actually measures the rainfall, total rainfall recorded, that actually measures, and based on this we can actually determine the intensity. So, how then at what intervals we should have, as we were saying that it is not only the intensity that varies over a particular rainfall event, but also we say that the area wise rainfall also varies. So, that could only be determined by putting rain gauge stations in every area. So, the rain gauge densities also plays an important role. So, the ratio of the total area of catchment to the total number of rain gauge stations in the catchment gives us the rain gauge density, and cities with population greater than 10 lakh, the rule is to put one rain gauge per 5 to 10 square kilometers. For 1 to 10 lakh, this is one rain gauge per 10 to 20 square kilometers, and greater than 1 lakh, one rain gauge per town. So, this is where we are generating the IDF curve. So, the first table that you see over here, this table, you in this this is the duration in minutes. So, 5 minutes, then 10 minutes, 15 minutes. So, this duration is 5 to 10 minutes, 10 to 15 minutes. In that way, these durations are given. And similarly, on this side, we have got the rainfall intensity. This is greater than equal to 5 millimeter of rainfall per hour, greater than equal to 10 millimeter of rainfall, and over these figures are the number of events that has happened, right. So, what this chart actually shows is, this chart is actually has to be done based on the data that is already available. We have to actually summarize that data and then do cumulative additions both horizontally and vertically, then only we get this kind of figures. So, what these figures signify? This means around 1965 rainfall events of duration 5 minutes had intensity greater than equal to 5 minutes. Greater than equal to 5 millimeter per hour. Similarly, for a duration of 120 minutes, 51 events were, or rainfall events were recorded, 51 instances you can say, where the rainfall intensity was greater than 5 minutes. So, obviously, if I go along in the same lines, that means greater than 10 minutes of intensity was observed for 32 events for 120 minutes. For if I consider 120 2 hours of duration of rainfall, then 17 events where we observed rainfall intensity greater than 15, and so on. And if I go the other way, smaller duration events like 5-minute events, we saw that rainfall intensity greater than 5 is 2000 events, almost all the events. Then as we go along, we see that around greater than intensity of 90 millimeter per hour, we saw 8 events. Greater than 75 millimeter per hour, we saw 20 events, but of duration 5 minutes. So, you see, the lesser the duration, higher is the intensity. So, using this particular table, we can create a stepped line for number of storms for 5-year storm return period. So, this data is a collation of data for 29 years, and this we are trying to determine the 5-year storm return period. So, for that we are determining this step line on this particular chart. So, this is for 5-year storm period. If it was 10-year storm period, we would have a separate step line. So, how do I determine that? So, what it means is, the required number of storm events having intensity equal to or more than the design intensity for once in 5-year occurrence for 29 years of rainfall data will be 29 divided by 5, that is 5.8 times on an average may exceed over a period of 29 years. So, more or less what it means is, that means because we are going for a 5-year return period and the total data is for 29 years, there is a chance that 5.8 times on an average the rainfall intensity may exceed for over that 29 years. So, if I take the value of this over here, we see that 8, which is for 90 for 5-minute duration, and this is for 90 millimeter per hour, this is 8, right. So, 8 times the event has occurred. So, at least this is more than 5.8. So, this is my first step. Then for the next 75, we see if over here we see 14 is the value, the next value is 5, right. So, we have to see greater than 5.8. So, this is 14 times 75 mm has happened. This kind of intensity have happened for 10 minutes. So, this is the next step. So, my step goes on like this, and same goes like this, and over here you can see that 45 millimeter of intensity for a 75-minute period happened 6 times over here. So, that means this is the step. So, this is how we construct the step. Now, the thing is, even though we are saying 8 times, 14 times, 8 times over here, but actually the value is 5.8. So, we have to do some interpolation. So, the time intensity values for this frequency are obtained by interpolation, and what we do is after interpolation we get this particular table where we have intensity duration for storm once in 5 years. So, we can see that for 25 millimeter per hour intensity, or we can go this way as well, for 90 millimeter per hour intensity the duration was 8.5 minutes. So, this is 90 millimeter intensity, duration was 5 minutes, but we interpolated because this value is 8, but we have 5.8. So, we can interpolate this value from within 5 to 10 minutes this duration will increase, and this we found to be around 8.5. Similarly, for 75 mm this value becomes 16.75. For 60 mm of rainfall this value became around 25.25. Over here see 60 mm 6, which is just a little bit above 5.8, and that means 25 will actually increase a little bit, that is 25.25, and then 55 becomes 60.5 and so on. Now, this is the data which could be correlated together, and we can establish the relationship between intensity and duration and frequency using this data. So, frequency is already chosen, which is 5-year period. If we have gone for a say 10-year period, then we would have divided 29 divided by 10, which is 2.9. So, in that case 2.9, the step would be something like this. Over here the steps would be something like this. So, in this way the steps would be different, and then we have to recompute this intensity values for a 10-year period. So, for different time periods or different frequency we can have different steps, and accordingly we can generate this table from where we have to establish a relationship between intensity and duration. This could be done through any sort of regression, right. So, how do we generate that relationship? So, for example, in Indian condition we use this Barnard equation for generating IDF curves, where the relationship that is proposed is I equal to A divided by T to the power n for Indian conditions. So, I is intensity of rainfall in millimeter per hour, T is rainfall duration, and the relationship is based on A divided by this relationship is A divided by T by n, where A and n are constants. So, we need to calibrate based on the data that is available to us. For example, in this particular case the data is 5 minutes duration, intensity is 123.28 millimeter per hour, 120 minutes duration 32.87 millimeter per hour. So, this data is available based on this rainfall gauge stations data. So, once this rain gauge data from this meteorological data, so once this data is available, we can do this we can fit this particular values, and we can determine the values of A and n. So, how we can do this curve fitting exercise? It is undertaken to determine the constants, and we can just convert take log of both sides, log I equal to log A minus n log t, and then we can determine the slope of the line is n and intercept on the y axis is a. So, based on that we can determine n and a. So, we can fit a linear line between these two between these points. We can do a cluster, we can plot this, we can fit a straight line, and then this a and n value based on the intercept and the slope of the line, we can determine that, and we can generate the relationship. And then using the relationship we can plot the intensity and duration, and this will result in this sort of a graph. And from this graph, this is the 5-year or whatever is the return period of this particular data. So, based on that we can say that this is the IDF relationship or IDF for storm of once in 5-year period. So, this is how we can generate a IDF relationship. Now, once constants are known, Barnard's equation can be used to determine intensities of various durations, thus generating the IDF curve for a particular return period. Now, this is all fine if we have this kind of data, and this data is the maximum data that is observed during the 5-year period for that duration of 5 minutes, 10 minutes, 15 minutes and so on. But if we do not have this data, what to do? So, already a lot of researchers have developed several empirical relationships, or they have done these investigations earlier, and usually they have given various formulas. So, one formula is I equal to A by T plus B, where A and B are constants which can be determined by calf fitting exercise, and this actually has been determined by some people, and we can directly use these formulas as well. But again, of course, if we do this kind of estimates, this would be very broad estimates, but actually if I want to plan a sewer network for a line, we really need to establish this IDF curves. So, what is this formula? So, maybe for solving problems or for some exercises we can use this, but actually in real life we have to go for IDF curves. So, the formula is I equal to 25.4 A divided by T plus B millimeter per hour, where A and B values has to be calibrated, where T is the duration of storm in minutes, A is equal to 30 and B is equal to 10, when duration of storm is 5 to 20 minutes, and A is equal to 40 and B is equal to 20 when the duration of storm is 20 to 100 minutes. So, that is how we are going to use this particular formula. So, A and B value is not fixed, but it varies as per the duration of the storm. So, we can directly use this formula as well. Now, Barnard's equation is pretty common in Indian context. We use this based on the data that we have got, but there are other methods as well. For example, as we know that this kind of rainfall events are probabilistic, so we can use a stochastic approach as well. So, we know that this hydraulic there is variability of hydraulic data, that means we are taking the maximum, but there is variation in the data, and so it is partly deterministic and partly random, which can be predicted using probabilistic methods. So, we can use like the equation that we have used earlier was Barnard's equation. It was following a certain formulation of that particular equation. So, similarly, we can use a normal distribution to determine the probability distribution, or a log normal distribution, or a Gumbel extreme value distribution, and the log Pearson type 3 distribution. So, these are the ones which are used, and out of this Gumbel extreme value distribution is the most common one. So, this is basically a curve which needs to be fitted with the data. So, we assume that this curve is, these are the curves which suits the data, this kind of data, this intensity duration data, and Gumbel extreme value distribution is the one which is most commonly used. So, how does the Gumbel extreme value distribution looks? It looks like this, and it is suitable for predicting extreme values in hydrologic and meteorological studies like maximum rainfall and so on, and this is given as x t equal to u plus alpha y t. X t is intensity for return period t years, then this x this would be x bar, this would be x bar. So, x bar is mean of n observations that we have for that particular return period for that particular duration. Alpha is standard deviation, which is x minus x bar whole square divided by n minus 1. Alpha is root 6 divided by pi into sigma. Yt is equal to minus log of to the base n into log of t divided by t minus 1. So, this t is the return period, n is sample size, and x is the rainfall event. So, this is the basic formulation that we have got, and now let us look at an example. So, suppose we have got rainfall data. So, maximum annual series rainfall depth data is available with us. So, this is rainfall depth in millimeter, right. So, this is for year 1979, 1980, 1981, 1988. For duration of 15 minutes, maximum value observed was 21.5. For 30 minutes, it was 25.5 millimeter. This 45, it is 32.5 millimeters. So, these are all in millimeters, right. So, similarly, when the years the more for all these years, if I now take the entire data, what we are getting is for 15-minute duration, if I take all the observations, so this becomes my number of samples. So, if I put this in the formula, okay, so this is maximum depth of rainfall of each rainfall event corresponding to 15, 30, 90 minutes interval occurring on one day, and then for entire year is recorded for 25 years. And we use the Gumbel distribution is applied to determine the IDF curve for a particular return period. So, let us assume that in this particular case we are considering this all this different data, and maybe this is a 5-year return period. So, 1, 2, 3, 4, 5, 6. So, there is 6 years. So, we can assume we can go for a 5-year return period. And so, over here we calculate the mean for 15 minutes, which is 22.96 out of all this data. For 30 minutes it is 33.45 and so on. Similarly, we calculate the standard deviation using the formula that I showed in the previous slide. Then we calculate value of A, then we calculate value of U, and then for t equal to 5-year periods, based on this particular data, we put value of 5 over here, we can calculate value of yt, and then xt value, which is given in millimeters of rainfall. For this particular duration, we get a maximum rainfall intensity of 28.08 millimeter of rainfall. So, this millimeter of rainfall is in for this particular time period. Now, we need to convert it into intensity, which is millimeter per hour. So, we will multiply this by 60 minutes and then divide by 15 minutes, right. So, this becomes 112.3. So, these are the different intensities for this time period, and if we can put it on the curve, it looks like this one, and this is the following the Gumbel distribution, we are able to join these points and we are able to create this particular intensity curve. So, this is how we create intensity curves using the Gumbel distribution or a stochastic approach. So, the concept of time of concentration, I have already discussed this concept. So, the time of concentration is the time required for water to travel from the most hydraulically distant point in the total contributing catchment to the point of consideration. So, if I have a catchment area like that and I have a drain, this is inlet 1, inlet 2, inlet 3, inlet 4. So, inlet 4, 3, 2, 1. So, what contributes to 1? This probably this is the area which contributes to 1. What contributes to 2? Probably this is the direct area which contributes to 2, and also water comes from this inlet, because all water goes from this catchment into this inlet. Similarly, and then the water also comes like this. Same happens over here. And then over here this water goes and reaches there. So, point of concentration over here is the time required for water to travel from the most hydraulically distant point in the total contributing catchment to the point of consideration. So, the total contributing catchment to this particular inlet is extreme point, probably is this one or maybe this one. So, what is the total time taken by water to travel over here? Then for this point, the total time required for water to travel from the most hydraulically distant point in the total contributing catchment. So, for this the total contributing catchment is the entire one. So, here again the distance could be either this one or this one, that I do not know. So, but usually we can assume that this one, because for this one it was this, because when the water reaches this inlet, it actually travels via this particular drain. So, the water which travels from the surrounding area plus the water which comes along the drain. So, there could be water coming from this side which is actually higher, it takes maybe larger time than water traveling from this point to the inlet and then along the drain. So, together, so we have to check which one is the highest and actually consider that as the time of concentration. Same goes for inlet number 3, 4 and so on. So, we generally assume that the intensity of rainfall as per the time of concentration. That means, whenever we are in the IDF relationship, we will consider that based on whatever is the time of concentration is for the particular inlet, we will take that time as the duration, and based on that duration we will determine what is the intensity of rainfall for whatever return period we assume for that particular point. So, maximum flow peak discharge may occur when only part of the upstream of catchment is contributing. So, we are assuming that the entire catchment is contributing, and whenever the entire catchment's water reaches the particular point, we may have the largest time of concentration, but it may not be true. So, that means the maximum flow may occur when only part of the upstream catchment is contributing. How? That is because the time taken, the total flow that is being being contributed is depends on area into intensity. So, the total rainfall that falls on that area into the intensity of rainfall. So, both are important, area and intensity. So, if the entire area is considered, it may take certain amount of time. At that point of time, the intensity may be some value, but if I take a smaller area, maybe the area is less, but the intensity is higher because the time would be less for concentration. So, that means runoff coefficient into lesser catchment area into higher rainfall intensity is greater than runoff coefficient into full catchment area into lower rainfall intensity for higher time of concentration, and for this one is lower time of concentration. So, this could be also happening. So, this is called the partial area effect. So, usually we assume that when the entire catchment contributes, that is the time of concentration, straightforward. But there may be some cases where we may end up finding that even though a lower, not the entire catchment, only a partial area is during a part of the catchment is contributing, the concentration time of concentration would be lower, but because of higher intensity at that point of that time of concentration, we may end up with higher flow. So, that could be a possibility. So, that is called a partial area effect. So, the total volume of water could be estimated via several methods. One is the rational method, which you have learnt already, but we will see how it is applied when we try to determine use rational method to determine sewer volumes. Then time area method, then unit hydrograph method, and then rainfall runoff process simulations. So, we will learn all this method in the next module. So, IDF curves are not readily available for all areas. In absence of data, empirical formulas can be adopted. Maximum discharge is estimated based on time of concentration and contributing catchment area. Intensity of rainfall is adopted as per this time of concentration, and intensity of rainfall also varies as per the return period adopted. So, these are the few points that you can consider when you determine IDF curves and select a return period, and also try to use it for determining the time of concentration and of course, the intensity of rainfall for that time of concentration. So, these are the references you can use. Thank you.